Okay, let's wrap up this discussion of Markov chains. We just saw that when we use our Markov chain to compute a joint probability, we are multiplying a bunch of conditional probabilities and a marginal, right? That's always what we're doing when we're computing joint probabilities. But there's a concern that crops up here because we're multiplying together more and more and more fractions, right? More and more and more numbers, probabilities, which are numbers between 0 and 1. And something eventually can go wrong when we do this. So let me just show you, this is a transcript of what would happen in Python if you made a series of products, right? So this very first one, this is just 0.5 or 1/2 raised to the power 1, right? So that doesn't do anything. It just gives us back 1/2 again. But now let's make some products of 1/2s, right? 1/2 just being an example of a probability. A probability might be 1/2. Right, so here's 1/2 times itself 10 times. So this is 1/2 raised to the 10th power. And what do we get here? We get something like 1 times 10 to the minus 3, right? A little bit less than that. Okay, now let's take 0.5 and raise it to the 100th power. So 1/2 times itself 100 times. We end up with something to the negative 31, right? So much, much smaller number, obviously. And if we do it to the 1000th power, we get something with negative 300 in the exponent, 302 in the exponent. And if we just go one little step further and take 0.5 to the 1100th power, we get 0. Not some really small number, like with, I don't know, negative 320 in the exponent or something like that. We get literal 0, like actual 0. So the result's equal to 0. And this is not true, right? Obviously, if we multiply together a bunch of numbers, none of which are 0, right? The answer can't be 0, right? So this is definitely not the correct answer. The reason we're getting this answer from Python, it's not a bug in Python either. It's just a function of the fact that in your computer, numbers are represented with a limited finite number of bits. And at a certain point, the bits aren't capable of representing the number that you need it to, right? So this is what's called underflow. So when we multiply fractions together, many, many, many fractions, we'll eventually get to the point where the number of bits that are allocated to the exponent, right, this part, will run out of bits, right? The exponent is getting more and more and more negative, and eventually we'll get to the point where we actually can't represent exponents that are negative numbers of a large enough magnitude, right? And at that point, the number gets rounded down to 0, which is why we call it underflow, right? There's a corresponding notion of overflow, which is when the exponent gets too large in the positive direction. But when the exponent gets too large in the negative direction, we sort of run out of options, right? We just don't have enough room to represent the answer, and so the computer rounds it to 0. For more details about how floating point numbers, which is to say decimal numbers, are actually represented in the computer, and why this underflow phenomenon happens at this particular point, well, you can read the specifications, the IEEE specifications for floating point numbers. There's actually, though, a really good Wikipedia article you can go check out that'll have more details. But this is a constant problem when you're dealing with numbers in a computer, right? They're always represented in a finite, limited number of bits, and sometimes that gets you into trouble. And this may seem like a sort of minor technical point, but if you are really going to implement Markov chains or hidden Markov models, which we'll talk about next, you run into this problem very quickly, right? So this is a very real, practical problem that we need a solution to. The solution that we'll use is a very common engineering trick that people use when they are multiplying many, many fractions together in a program, which is to switch to the log domain. And so what I mean by that is, instead of just dealing with raw probabilities and multiplying them together, we do everything in log space. So we just take the logarithm of everything that we're doing. And instead of multiplying together fractions, we are adding logs of fractions, right? Because the log of a product of these fractions is going to be a sum of logs of these fractions, right? Just by the rules of how logarithms work. All right, so when we have the logarithm of a large product of fractions, that is also a sum of logs of the constituent terms of that product. We can summarize that with a summation like this. We still have to have this separate term for the marginal, right? So we still got our marginal over there, which is now a log probability. And so this is what we would get if we switched to the log domain. Just assume for the moment, because this is a very natural thing to do in the computer, that all the logs are base 2. All right, so in the specific examples I'll show you, the logs are all base 2. It's not so important what the log base is, but just assume that they're base 2 here. Okay, so if I take that same Markov chain, that same table of 16 conditional probabilities that I had before, trained on examples that came from inside CPG islands, I can just log it, right? I can take the element-wise logarithm of all the numbers in that table. And that's what I'm doing here with numpy, right? I'm taking numpy.log2 of that table. I have a new table. These are now all log probabilities instead of probabilities. It makes sense that they're negative because the probabilities are all less than 1. So the logs of those probabilities should all be negative, and they are. Okay? And so if I want to compute a joint probability, just like I did before, instead of multiplying together the probabilities that I look up in this table, I of course am now going to add together log probabilities, which I look up in this table. And I'm just going to go through essentially exactly the same procedure as from the previous lecture. It's just that I'm adding log probabilities instead of multiplying probabilities. And at the end, I'll get this answer. And if you do the math, right, if you just plug this into Python, you'll see that 2 raised to the power negative 8.892, which is what we got as our log probability at the end of the day, is equal to the same number that we computed in the previous lecture, which was 0.0021. Okay, so at the end of this sum, you get a log probability, but you can always re-exponentiate it, take 2 to that power, and you'll get back to a probability rather than a log probability. Okay, so switching to log space is a good way to get around this issue, and we can always come back, right? We can always exponentiate, which gets us back out of log space, back into the normal space of probabilities. Okay, and these logs are sufficiently, the sum of log probabilities is not going to run into that same problem with running out of bits in the exponent, because that exponent does not go up as quickly, nearly as quickly, when we are dealing with the logarithms. Okay, so that's one issue we wanted to get out of the way. The next thing I want to discuss, and it's actually kind of convenient that we have this log trick for this discussion, is our whole goal was kind of to compare whether sequences seemed to come from inside or from outside CPG islands. And we've already shown on multiple slides up to now 2 different Markov chains, right? A Markov chain of 16 probabilities that we computed on examples from inside CPG islands, and then another 4x4 table of conditional probabilities that are computed over examples that came from outside CPG islands. So we've seen these 2 tables up until now. And so if we want to be able to come to a decision, if you give me a new sequence and I want to decide, does that sequence look like it came from inside or does it look like it came from outside? One strategy might be, I'm going to compute the joint probability of your sequence, of that sequence, under the inside model. And I'm going to compute the joint probability under the outside model. And then I'm going to compare. And the way that I'll compare is to take a ratio. So I might, given a sequence X, I might compute the joint probability of X using the inside model, and then compute the joint probability of X using the outside model. Take this ratio, and if the ratio is greater than 1, that's telling me that the probability with the inside model was higher. If the ratio is less than 1, that's telling me that the probability with the outside model was higher. So it gives me a strategy for picking which I think is the better hypothesis, inside or outside. Okay? Because we're dealing in log space, instead of thinking of the ratio, p of x for inside, p of x for outside, we can think of the log ratio. We can take the log of the ratio of the probability under the inside model over the probability using the outside model. And if we do that, then instead of asking whether that ratio is greater than 1 or less than 1, we would ask whether the log ratio is greater than 0 or less than 0, right? That would be equivalent, right? So for example, if the probability of x from the inside model is twice as high as the probability using the outside model, then the ratio, forget about log for a moment, the ratio would be 2, and the log ratio would be 1. If we flip it around and say, what if the probability under the outside model was twice as high as the probability under the inside model, the ratio would be 0.5. The log ratio would be -1. Okay? All right. So let's just say that the score that we're going to use to decide whether a sequence seems to come from inside or outside is going to be this log ratio. Right, the log of the ratio of the probability of the sequence under the inside model over the probability under the outside model. And let's just do a little bit of math because we can rearrange terms a bit in a way that's favorable to us. So if we take the log of this ratio, well, the log of a ratio is a difference of logs, right? So the log of that ratio is the log of the numerator minus the log of the denominator. Great. So far, so good. We just turned division into subtraction. That's usually a good idea. And those two logs in this difference, they are each themselves sums, right? So the sum of that probability of inside is the sum of a bunch of logs of each of the constituent conditional probabilities. Same for the thing on the right-hand side of the minus sign, right? So each of those two things is a sum of logs of conditional probabilities. I'm going to ignore the marginal probabilities for this discussion because they really just don't add much. So forget about them for now. Okay, so I've got these two sums. The sums are over the same range. They're from 2 to k. I can actually pair off the terms of these two sums. So I can take the I equal 2 term for both sums and sort of factor them out. And in some sense, I can sort of invert the order of the sum and the difference. And I'll end up with a sum of differences of logs of conditional probabilities, right? So this is just a refactoring of what was on the previous line. So I can sum from I equal 2 up to k the log of the conditional probability under the inside model minus the log of the conditional probability under the outside model. And in this way, this score, S of x, ends up being computed as a sum of log ratios of conditional probabilities. So now we have a sum of log ratios. What's nice about this is if we know that this is what we need to compute at the end of the day, if all we really need to compute is this S of x, this scoring function, then our table only really needs to consist of log ratios of conditional probabilities. So we really just need, instead of having separate tables, one for inside, one for outside, we really just need one table of log ratios. And we're going to sum together those log ratios in order to compute a score for a sequence. Okay? So thinking of it in terms of Python, if I have my, this first table, the one on top is these are the conditional probabilities, not log probabilities. These are just straight up conditional probabilities from inside CPG islands. These are from outside CPG islands. Now I'm going to, all in one line, I'm going to take the log ratios. So log of the first table, element-wise logarithm of the first table, minus element-wise logarithms of the second table. I get a combined table now. This combined table, notice it has some positive numbers, some negative numbers. Makes perfect sense. These are now log ratios, right? These are now differences of log probabilities. So some of them are going to end up positive, some negative. And if I want to use this model to score a sequence, no problem. It's just like we did before with the individual models. We either multiply together probabilities or we add together log probabilities. This particular model is log ratios, so we're going to add them. And so for a given sequence, we can add together the corresponding numbers in the table and we get a score. And whether that score is positive or negative is our indicator as to whether that string came from inside or outside a CPG island. So a negative score in this case indicates this seems to have come from outside a CPG island. Okay. All right. One quick thing to mention, we had a discussion in the previous video of we looked at the probabilities for the outside CPG island model, and we said, does something in this table look unusual? And we said, yeah, one of the probabilities is low. Well, we can play the same game with this table. Do we see something that looks unusual? And in this case, what we see is an unusually high number here. That, again, is probability of G given C, right? So that's the log ratio of the probability of G given C, log ratio in the inside model versus the outside model. And it's positive, right? 2.6 something. So it's, of all the numbers in this table, this one has the highest magnitude and it's positive. And that makes perfect sense, right? Because again, that element of the table corresponds to observing a C followed by a G. We're looking for CPG islands. So the log ratio of observing a CG inside versus outside should be high, right? We should see way more CPGs inside islands than outside, so that probability should be high. Okay, so that makes sense. Okay, so we've kind of deferred the question of whether the Markov assumption is okay to use in this situation. A couple of videos ago, we looked at a few different situations and we said, okay, well, Markov assumption is more reasonable here and less reasonable there. It's time to take a look at whether the Markov assumption is going to work for detecting CPG islands or not. And first, we'll start with a couple of sanity checks, right? So let's just do some very simple checks to see, does the score S of X actually give reasonable results for extreme examples? And so here's a very extreme example, right? I'm going to compute the score of a string where that string is nothing but CG packed in tightly several times in a row. Okay, so if my score is doing what it should, my score should say, oh yeah, this really looks like it comes from a CPG island. It should give it a very positive score. Okay, which it does, all right? So it gives it a score of 32 and change, 30, positive number, large number, great. All right, if we give it another example, this one, it's a mix of bases. It's got A, T's, and C's, but there's no CPGs. None. In fact, there's no G's at all in this example. So we hope if our score is doing its job, it should give us a negative number for this one, and it does. Okay. So it passes at least this very simple check. But the real question is, what happens if we throw lots of realistic examples at this model? Very simple model, very simple Markov chain model. So how well does this score S of X distinguish strings that are drawn from inside versus outside CPG islands? And I'm going to have one set of data that I use to train, to come up with the Markov chains, and another set of data that I use to test, to see whether that Markov chain is doing a good job of distinguishing inside from outside or not. All right, so I trained this on data that's from one human chromosome, chromosome 22, and I'm going to apply it to examples that come from another chromosome, chromosome 1. And I'm going to plot, because I know for each of these examples whether they're from a CPG island or not when I go to test, I can draw on this plot two histograms, two distributions, a red one and a blue one. And the red one is going to be the examples that are from outside CPG islands, and the blue one is going to be for examples that are from inside CPG islands. So let's just think about what we want this to look like, or what this could look like, this plot. This plot that's going to be a sort of superimposed two histograms, one red, one blue. If our score is not doing a good job, then I suppose what we expect to see will be something like two distributions kind of right on top of each other. All right, so these are just In other words, the score is not distinguishing them. You can't tell. Whether the score is positive or negative is not a good indicator of whether the sequence came from inside or outside a CPG island. That's one possibility. Another possibility, if we're doing a fantastic job, would be strong separation between these two. Very strong. Almost no overlap. Maybe no overlap at all. That would be ideal. Maybe not realistic though, right? Because our notion of a CPG island is a little bit squishy, right? There should be examples that kind of don't exactly go cleanly in either category, and where we're going to make an assignment mistake in practice. The reality is sort of somewhere in between those two possibilities. We do have two distinct and distinguishable histograms here, but they do overlap, right? They do overlap in the middle, which means there are some examples that our score is not correctly able to distinguish. There are some inside examples that get negative scores and some outside examples that get positive scores. But as we look at this, the main thing I want you to take away is that the Markov assumption in this case really did fine, right? It didn't do a bad job. If the Markov assumption was really, really bad, if that Markov assumption was not something we should use in this scenario, we would have seen these two histograms kind of on top of each other and almost no distinguishing power based on whether the score is greater than 0 or less than 0. Looking at this, I would say this is about as well as we could hope to do, right? We can't have perfect power to distinguish inside from outside, but we have very, very good power. And that's with the Markov assumption. In other words, every time we go to compute a joint probability, and this score depends on joint probabilities. Every time we go to compute a joint probability, we are forming that joint probability by using the multiplication rule to create a bunch of conditionals and a marginal, and then throwing away a whole bunch of after the conditional terms from those, using the Markov assumption. Right? The Markov assumption says, if you tell me about the previous, it doesn't tell me anything in addition if you tell me about even further. So it wasn't clear whether this was going to be a good assumption for this kind of data or not, but as this example shows, it was a reasonable assumption to make here. And so this is our first sign that for applications in genomics, for analyzing DNA, using the Markov assumption can be perfectly fine, and this is a good example where it did work. Okay, so that's what we have to say about Markov chains. In the next video, we'll move on to hidden Markov models.